trickier or not. So we'll just grab this one. So it was this little cage. So we've got the reactions, and I'm just keeping in mind that what I was talking about before, this is the total weight, so this is the total reaction at that point. If they'd asked me for the tension in the cables, I'd need to remember to divide that by 2. And if they'd asked me for the reaction at one of these connections, let me go back up here and show you. So there's 2 cables. Similarly for the connections, there's 2 connections, but I've used the whole weight. So if I was asked for the forces at the connection, at one of the connections, I'd have to divide that by 2. Right, so same again. We'll start off just doing the X and Y's, X and Y components. And if we're going to do that, so just thinking ahead, if I'm going to do that, I'm going to have to figure out what the X and Y components are of this force. So we don't have that at the moment. I might just have to move that angle out of the way. How annoying. Come on, there you go. I'm doing it in grey because I've already used all the other colours. So let me just do that. So I need the components of this. I might have to move this as well. I just want to be careful when I'm doing these, just to draw the components at the right point of application so I don't get confused about the moment that they're imposing. So we've got, what have we got? R1Y, R1X, and just to find the value of that, I've drawn that a little bit too long. Let me just do it, better fix it. So went a bit too far, so it's about there. That was R1X, then up this way we've got R1Y. R1Y. Right, and I'm looking at this, X is in the negative direction, just keeping that in my mind. So therefore, we'll calculate the X and Y components of this force. I'll just speed through that. I'll get you on the other side. So I have got myself those components, and it'll be, I don't know if you'd have to do that. You might be able to just say R1X and R1Y. I found them in terms of R1 itself, but let's just push on through and we'll see what happens, and we'll figure out what we need to do as we go along. So I'm just figuring out the X and Y components. We don't know R1, so I can't get these down to a number. They're just ending up being a formula or an equation. And we'll just go a little bit further and see if I actually needed to do that or not. So let's try and do, I don't know what I want to do first here. So we've got R1 here, so I'm just thinking, let's just try something and see. So sometimes I once tutored a student, and just the one thing she needed to know to get up and running was with maths. Oh, let's not use OneNote for a start. Let me just figure that out, right? Oh, why? Okay, let me pause. Was that you don't need to know what to do next. Sometimes you just need to try stuff and just see what happens. And then you'll usually figure it out after that. So it's not necessarily the case that you're going to know exactly what to do for the next step. So sometimes you just have to try what you think might work, and then from there you'll usually figure out what you do need to do. Anyway, so let's start off with the X components of force. So the sum of the X components must be equal to 0. So what does that tell us? Well, that tells us that, now let's get the directions right. So R1X is negative. Okay, so that's going in the negative direction. And I probably should have put that here, but as long as you get it right in the equation or at the end of the day, so this should really have been minus 0.342, sorry about my writing, 0.342 R1. This should be R1X, this should be R1Y. R1Y is going in the positive direction, so from now on we're just going to use these in their standard directions, so that's going to be X and Y that way. So that's positive, so that one's okay. So let's come back again to here now. So fx, sum of fx is equal to 0. So that means that r2x is positive. So r2x, and what other x's I've got? Minus r1x. I think that's the only other x I've got, is the x associated with this. So it turns out I chose the right one after all. So is equal to, oh sorry, take away, so it's the negative direction, take away r1x is equal to 0. Therefore, maybe it doesn't help much, r2x equals r1x. Fair enough. I'm just trying to think about whether to substitute this in. So we've got r2x equals r1x. We could substitute this one in, r1 cos 70, but let's just see what happens first. So we know this must be equal to that. So that's all good. And I think we may end up with simultaneous equations on this one. Maybe wasn't the best example to choose for an early example, but let's try it. The sum of fy is equal to, so we've got to add up all the y components now, just taking care with the directions. And I guess this maybe is where we should have started, because it's the only one we've actually got a value, this one. But those must be equal to 0. So that means that r2y is positive, so it's going up the way. So r2y minus 1.962 kilonewtons for the weight. That's down the way. And r1y is also positive, it's going up the way. So plus r1y is equal to 0. So therefore we're going to get r2y plus r1y is equal to 0. Now, we've got some simultaneous equations. That's one. We've already got, oh no, that's x. Excuse me. Yeah, so we're going to have to do some more on this. So what I'm thinking at the moment is I've got r2x, r1x, that's 2 variables so far, and then I've got r2y, r1y, that's 4 variables. So I can't solve those with a set of simultaneous equations. We're going to have to substitute these values in, maybe. And then what happens if we do that? Doesn't really help. How many unknowns do we have here? 1, 2, 3, 4 unknowns. So it's a statically indeterminate problem. So we can't solve it. So I'm just thinking here, we've got this force we don't know, this force we don't know. Those are independent of each other. We've got this force we don't know, this force we don't know. So we've got 4 unknowns. You could think of that as we don't know that magnitude and we don't know its angle. So that's also 2 unknowns there. And we've only got 3 equations. We've only got 3 equations. Therefore, we are not going to be able to solve this. There's no solution for that using the theory we've done so far. You can solve it other ways, but you can't solve it using the theory we've done so far, which is surprising. Would have thought you could. Maybe I can, because this is going to depend on that. I think I could find a way. This is too hard to start with. And that's equal to 0. And so now we're looking at that, just seeing are we any further on. And so it looks like we've got 2 simultaneous equations, but we haven't really, because we've got r2x, r1x, r2y, r1y. So those are all 4 of them are different. We could substitute this stuff in. That would just get us r1 here. That actually kind of gives us an answer, but not by a way you know. So the fact that we know, where did I get r2x? No, it doesn't. So I could substitute, we've got r1x up here, but we don't know anything about r2x, so it's not going to help. And so I can't see a way that I can solve those either, because there's too many variables. To get simultaneous equations to work, we'd have to figure out a way to get only 2 variables and 2 equations, but that's not what I've got here. So I'll just keep plugging on, see if the final equation helps us. So we know the sum of the moments is equal to 0. That's the last equation. So we've got 3 equations for these. Sum of the x components is 0, sum of the y components is 0, and because it's not particle equilibrium, it's rigid body equilibrium, the sum of the moments must also be 0. So let's try the moments. For the moments, you have to choose a point. You can choose any point, but it tends to be best to choose one that will eliminate as many forces as possible. So let's choose this one here. Why does that eliminate those forces? Because those forces have no lever arm to that point. Therefore, they've got no moment to that point, so they won't appear in this equation. These two will, though. So let's have a go at that. So we know that that will mean, let's think about the moments here. So we've got R1x is going this way. It's got a lever arm of 1 meter. The perpendicular distance between this force or the line of action of this force and that point is 1 meter. If you can't see that, just trace the line of action to see where it is. So it's coming back here like that. That's the line of action of that force. And so it's this distance here from A up to that line, which is the same as this distance here, 1 meter. So therefore we're going to have, that implies, oops, wrong color. That implies, so R1x times D1x, so the lever arm for that. And now let's think about direction. So we've got this point here, so that force is going to want to rotate that anti-clockwise. So it's going to go anti-clockwise. So therefore that's positive, so that's all good. R1y is also going to want to make it go anti-clockwise, so that's going to be positive. And it's going to be R1y times D1y. And that's all going to be equal to 0. I think I spotted a mistake up here. Where was the mistake I spotted? It's this one. Sorry about that. I lost my 1.962 somewhere along the lines. Okay. Does that help us? Well, we've got 2 equations. Oh well, let's just put in what we know first. So that's going to be equal to R1x times D1x, just 1, plus R1y times D1y. So the distance, so the line of action is here. Perpendicular distance to the line of action is here, so it's times 2.2. So it's R1y times 2.2. And you might hear that I'm cheering up a bit because I think I can solve this now. So we've got an equation, it's got 2 variables. Excuse me, so we wouldn't be able to solve that. However, we've got a rule to reduce it down to 1 equation. So we've figured out this stuff up here already. We figured out R1x and R1y. Another thing we could have done would just be to find the lever arm to that. We could have found that value, but it's going to be finicky though to try and get that, or is it? Not really. No, it is. Sorry, just thinking about different options. So where are we here? What we've done is we've tried all 3 of the equations we've got available. I tried the wrong 2 first, but this third one is promising because I've got 2 variables, but I can reduce those down to 1 variable using these equations. Okay. Now, I've already thought about the direction of this, so I'm not going to worry about the fact that this is negative. I've already thought about the direction of this. So that's going to mean 0.342 R1, and then it's just times 1, so it just stays the same. And then, so that's from this one, we're substituting in R1x equals R1 cos 70, which ends up being this. And then we've got R1y is equal to 0.9397 times R1y, and we're going to multiply that by 2.2, equals 0. So therefore, we can just work all that out now, can we? So we just end up with R1, everything equals 0. Spot the idiot. What have I missed? So it's the sum of the moments is equal to 0. I've done these moments. What have I forgotten? I've forgotten the weight also makes a moment about that point. And so you've got that force going down the way. It's got a lever arm of 1.4 meters. That's the perpendicular distance. So we need to stick that in the equation as well. Plus, oops, positive or negative, it's going clockwise, that one, so it's negative. Negative 1.962 is equal to 0. Negative 1.962 is equal to 0 is equal to 1.962. Let's figure what that is. So we've got 0.342 plus 0.9397 times 2.2. So that's 2.409 to 4 significant figures, because we might have to use it again. That one's not R1Y, it's just R1. It's just R1. Okay, so I substituted in this into here. So 2.409 R1 is equal to 1.962. Therefore, R1 is equal to 1.962 divided by that. So 1.962 divided by 2.409, which is equal to 0.8144. So just so I'm not losing you, so I don't want to stop doing this because I think it's useful for you to see the process can be a bit bumpy to get to the right answer. I don't know exactly what I'm doing right to the end. I'm just trying different things to see what works. And so if I'd been smarter, I could have figured that out to start with, that I'd need to use this one here, but I wasn't, so I couldn't. So I just started figuring out some different stuff, see what works, then look at the 3 equations, see if I can figure it out. So I now know what R1 is equal to. That means I can figure out R1x and R1y. Once I've got those components, it should be pretty straightforward to substitute those into here, and we'll get our answer. Yep. So therefore, R1x is just going to be equal to, well, here's our formula up here. R1x is equal to R1 cos 70, so it's 0.342 times R1, and it's in the negative direction. It's negative direction, that makes sense. So negative 0.342. Is that right? Just check that, cos 70. I'm just checking that I haven't forgotten to round it. No, it was 3420 times R1, which is equal to, so we've found out R1 now, so it's minus 0.3420 times 0.8144, which is equal to minus 0.2785. And what were we in here? Kilonewtons. Kilonewtons. Maybe should have kept it in newtons actually. Too late now. And then R1y is equal to, so it was this one up here, it was just sine 70. I'll just check that again, just to make sure I've got that right. Yep, 0.9397 is correct, and it's positive, so it's 0.9397 times 0.8144 is what R1 is from over here, which is equal to times 0.8144 equals 0.7653 kilonewtons. Or we could have said, what could we have said? 765 newtons, something like that. It might be better to change this back. So it's equal to 278.5 newtons, and this is equal to 765.3 newtons. R1y and R1x done. Therefore, we can now figure out what these are. And so R1x, so that's going backwards that way. The only other x we've got is R2x, so it's going the other way. So R2x is just equal to, oh, I've lost a negative. And so therefore, R2x is equal to 278.5 newtons just from this equation up here. Where were we? Yeah, and R2x is going in the positive direction. So R2x is in the positive direction, that's okay. Just having a look at that now, just depends, that's okay. And now the last thing we need to get is R2y. How on earth are we going to get that? Well, R2y is just equal to R1y, R2y plus R1y is equal to 1.962. So therefore we've got R2y plus R1y equals 1.962. And we know R1y, that's it here. Oh, that's kilonewtons, so let's change that to newtons since we're putting everything back into newtons. 1962 newtons. So therefore, R2y is equal to 1962 newtons. Take away R1y, 765.3 newtons, which is equal to 1962. Take away 765.3 is equal to 1197 newtons. So reactions are R1x is equal to negative 278.5 newtons. R1y is equal to 7653.3 newtons. And that means that, we could just say R1 is probably what they might be looking for, 0.8144. Oh, sorry, change it to newtons. So just equal to 814 newtons. R2x is equal to 278.5 newtons. And R2y is equal to 1197 newtons. And that's just got all the answers, so you just say as per above sketch. Wow, that was a monster. And no doubt I've made a mistake in there somewhere. You can let me know where it is. Let's go back through really quickly because it was such a prolonged process. So what we're looking at there is I just tried different things to see if I could figure out all these forces. In the end, I should have realized to start with, but it was the sum of the moments that got me to an answer. But I did need to do this as well. So I figured out the sum of the moments, and then I realized, look, I can get that down to one variable because I can write R1x and R1y both in terms of R1. And so then I could solve that for R1. Then I could figure out the x and y components of R1 because I know that angle, so I can just use trig. In fact, I'd already got those equations up here. Once I knew that, well, I had my equations already from here and here that would let me figure out the R2x and R2y once I knew R1x and R1y, and so therefore got ourselves to a solution for everything. Phew.